Oh, hi. Welcome to the bonus episode where we will be talking about only one problem, which is the problem 20 from AMC12 paper A from last year. So just now, just last November, I think. It says like 2 points. P and Q are chosen uniformly and independently at random on sides AB and AC of equilateral triangle ABC. So yeah, and which of the following intervals contains the probability that the area of APQ is less than half the area of ABC? So what is the probability that APQ is less than half ABC, and what is the right interval? So draw a equilateral triangle. I don't see the fact of this triangle being equilateral actually helps, but let's just use it to make the computation simpler. And let's say BC is 1, okay, let's say BC is 1 and Q is somewhere here maybe, and Q is somewhere here, and P and Q, we have APQ. This is the triangle in question, which has the same corner with ABC, and we want APQ being no more than half ABC, or in other words, AP times AQ is less than half AB times AC. And AB times AC is basically 1 times 1 according to our assumption. So this is a half, and that's it. And what else can we do? Now, okay, I would say the regular method or the natural way of thinking is to do some integral. That is, when P is moving, what values can AQ take? But there's one caveat. That is, if P is close enough to A, Q can even go beyond AC, if you really think about it algebraically. But actually, this is not allowed because both points should be on the sides. That means if P is close enough, and if you really do integral, it can explode. You are considering more than what you should. So we have to split the whole thing into two cases. Case 1 is that P is above the midpoint here. This is a half case thing. So let's say case 1 is P above the midpoint. If P is above the midpoint, wherever Q is, on segment AC, the case is a good case. The thing is good for us, so it should be counted. And the total probability of case 1 happening is a half. P just need to be above the midpoint. So in this case, the probability is just a half. Okay, so case 1 is basically done. And now let's go to case 2. Case 2 says, of course, the opposite, P is below the midpoint. And in this case, we need to consider, because if P is below here, then Q can't be anywhere. Q have to be close enough to A to satisfy this inequality. So here comes the integral. If X, let's call this as X, AP is X. And if X is start from the midpoint, meaning half, and go all the way up to 1, and in each case, the weighted value should be no more than, according to this, it should be no more than 1 over 2x, and the total value you could pick is 1. So this is a satisfactory range. This is the whole range, dx. And now let's just do the computation. It is half. From half to 1, it is 1 over x dx. And then it is something like this. And then you're gonna find the difference, which is a half. And the first part is 0, the second part can be reversed. So it is just a half ln 2, and that's it. So this is the probability for case 2. Let's say PR. probability here. So what is the total probability? Just to have a look at this. This is half, I mean the probability for case 1, and here we've got the probability this for case 2. So the total probability, let's say, is just the sum of these two. This is a half, and this is a half ln 2. Okay, this is what we call an exact value, exact probability of this happening, But the thing is that, which one should you choose in this case, right? You have this, right? We already have total control on this, but can you pick the right thing from this? Maybe not this one, maybe not this one. Maybe it's easy to tell, but how about these? Which one would you pick, right? This is the problem. So actually this value doesn't help much. And you might say, okay, I just know what ln 2 is. If you really know this, then of course you're lucky. But to be honest, I don't actually know the value of ln 2. And if I really want to make a good estimation, what can I do? Taylor's expansion. But come on, it's just the AMC. I don't think this is how the problem is designed. We're not supposed to use that. Not even integral. But anyways, if you really want to use integral, I mean, it is quite natural to use it if you know how to do this. But if you have this, actually it is enough. You don't actually have to really do the integral and go all the way up to here. Actually, this only make the matter worse. This should be enough, because here we've got a function, and this function should be enough for us to use. You have this. Let's plot the graph of this function. Here it's 1 over x, so not hard to plot this thing, and it's from half to 1. So it is from half to 1. At half, it is a 2. It is half to 1, and so basically the integral part here, without this, okay, the integral part here is just the shaded part, the area of the shaded part. And what is the area of the shaded part? If we really want to make a good estimation, then we can cut it like this way, right? This is 1, and here we can connect these two dots. This is a diagonal, and the shaded part is within this triangle. It is containing this triangle strictly, so it is less than half of a half, because each box, it's actually not a square. It just looked like a square, but actually it's not a square. It's not a great graph, but yeah, it is half 1 over 2, because it is like 1 over 2 times 1 is 1 over 2, and this part, the top part, shaded part, is no more than 1 over 4, because it's all below the diagonal. So in total, that should be below 3 over 4 in total, the shaded area. And since there is a 1 over 2, so in total, this one should be no more than 3 over 8, and then plus 1 over 2. So the total should be no more than 1 over 2 plus 3 over 8. That is 7 over 8. So the total shouldn't be more than, strictly lower than 7 over 8. On the other hand, we have at least 1 over 2 here. And 1 over 2 times 1 over 2, this is 1 over 4. 1 over 4 plus 1 over 2, that is 3 over 4. So at least we have a 3 over 4. So the range should be between, actually here it is, over 3 over 4, but no more than 7 over 8. D is the correct answer. If you can just use this instead of this, right? If you end up with this and you think of something like Taylor's expansion, and you still get it, but it costs too much time, and this is not actually what we are supposed to do. This is way better. You have this, just consider the graph, and you have this. And if you have this, I mean, if you realize that you can use this trick, you don't even need to use integral. You don't even need to use a calculus. Just to consider this again. Let's say this is x, and let's say this is a y. And all we need is that x times y is no more than 1 over 2. And x is between 0 and 1, and y is between 0 and 1. Okay, here gives something pretty nice. Okay, now let's apply this trick once more, but this time it's just a one-off thing, just once, and the whole problem is done. Here, x times 1 is no more than 1 over 2, so this is This is the graph of x times 1 is 1 over 2, okay? And everything should be below this, this curve. And x is between 0 and 1, and y is between 0 and 1. That's the thing. We pick 1x from 0 and 1 uniformly at random, and pick 1y from 0 and 1 uniformly at random. And how many pairs of x and y can make this true? That's the question. And I would say everything within this shaded area would be a good pair. And what is the probability? Again, you're gonna complete this whole box, but connect these two dots. Okay, what's this? A 1, right? 1 over 2. So it is just a 1 over 2. For the same reason, this is 1 over 2. Okay, so easily you will notice that 1, 2, 3, 3 pieces here. It is more than 3 over 4. So it is more than 3 over 4, but not enough to make this triangle. Not enough to complete this triangle. So if you consider this triangle and the other 3 pieces, this is exactly 7 over 8, but you are just below it. So easily the answer to this problem is D. You don't even need to use integral, but if you realize that, you can use this. But yeah, so this is actually the smart way of doing this problem. In a hindsight, you would say, okay, this is also quite natural, but I would say most people would naturally think about doing integral and then end up with something like this. This is not really good, but at least what you can do is reconsider this thing and see if you can use the graph to help you decide, make a good enough estimation, and find the right choice, right? Just because this is the multiple choice question, MC question. Otherwise, this should do. However, you are forced to make an estimation. That's why this problem is actually interesting. And that's the end of it, I think. And I hope I will see you soon in a regular video on maybe Euclid or something like that, a Canadian contest. All right, that's all for today, and see you for now.